So first we used our infinite impulse response filters to generate this impulse response, but now what we're going to do is to implement using a recurrent neural network, also called RNN. In IIR filters, we have the delay chain of delay elements c to the power of -1, which delay each sample by one sample interval. In a recursive neural network, instead, we have the hidden states h, which is a vector or an array which is updated after each sample interval according to the matrix equation given here. So we have a tan h function here, we have some weights, we have some coefficients. So x of t is our input signal, here the impulse. T is our integer valued time index, which was n for the IIR filter. Then we have W, that are weight matrices. We have these coefficients B, which are the biases, and we will not use them. We don't need them for our purpose. Observe that X and H, they are column vectors or arrays. And also we have the non-linearity. By default is the tan h function, but it can, as an alternative to the relo function, that can also be used. And here from PyTorch documentation, you have a class recursive neural networks that will apply multi-layer element RNN with tan h or relo. That can be also used as an alternative. And for each element in the input sequence, each layer computes the following function, which we have it here. You can read more. Very important to understand the documentation, implement things. Since our IIR filter does not have a non-linearity, we choose the tan h function and keep the signal small such that it stays in its more linear region. So you're familiar with the tan h, so the function that goes from -1 to 1, and it will so values that are bigger than 1 or smaller than -1, they will be, let's call it, shaped to this tan h function. But if we keep the signal small enough, it will stay in its more linear region and we will avoid some problems. The hidden state h also represents the output of the recurrent neural network. So to make it function like our IIR filter, we use the hidden states as the delay line in our IIR filter, which means that the hidden states are equal to the filter output and its two delayed versions. So here we have this equation here, hence I equals to 0 denotes the most recent sample. And we have I going from 0 to 2, so we have values for I equals to 0, 1, and 2. And I0 denotes the most recent sample. Observe the notation ht of I, and this is an array or a column vector with 3 entries indexed with I at time t. From the time domain difference equation number 2 that we saw earlier, we know this here, which is equal to this one here. So then we have now relationship between the output, we have our input, here we have this hidden state h t. The h of t of 0 is equal to the I of t is equal to x of t plus a coefficient a1 times y of t minus 1 plus a2 times y of t minus 2. And then we have this equation here now without the y of t, but we have the ht of 0. Then we just need to shift the remaining hidden states by one time step down such that they become the delay line. So ht of 1, it will be equal to h of t minus 1 of 0, and ht of 2 will be ht minus 1 of 1. So now, with those equations in hand, we have the necessary weight matrices W of HH and W of IH, and in our simplified recurrent neural network update equation becomes is here, where we neglected the nonlinear activation function and we set the biases to 0. From here, we are now here. Then we will get our weight matrix W of HH, and we have A1 here, A2, 1, 1, and zeros elsewhere. So we set x of t as the single sample x of t instead of a column vector, since we don't need past x values because we chose no IIR part with L equals to 0 in equation 1. Hence, W of IH just becomes a column weight vector which has a 1 in the position for HT of 0. I have here the W I of H. And this is now our recurrent neural network working as our III filter. So the output of our recurrent neural network IIR filter is HT of 0, which we obtain by adding a linear output layer which has a factor of 1 for this element and zeros for the other elements.